Good morning, everyone. We are recording now, so we're all ready to get started. Hope everyone had a good weekend. Okay, well, where are we now? We are just going to wrap up the section on planes, so how to describe planes and how to work with planes in 3 dimensions. And then we will get into the next topic, which is chapter 13, vector valued functions or space curves. And so the idea is that we're dealing with lines and planes right now, and then we're going to look at how to deal with more general type curves in space. And then we'll get into the calculus. We'll come back to section 12.6, which is on quadric surfaces. We'll come back to that a little bit later. I want to get more quickly into the calculus part of the course. So let's look at where we were at the end of last day. We were just working on example 9C, so this one here, and we wanted to find the equation of the plane that passes through the point 246 and contains the line which is given there. The line is given in parametric form. So the first thing we want to do is we want to say, well, we know a point on the plane. We also want to know a couple of vectors in the plane, or we want to know a normal vector to the plane. That's an alternative. And then given 2 vectors in the plane, of course, we could find a normal vector to the plane by taking their cross product. So that's the route we're going to go. Because we're going to say, well, we've got this point P in the plane. We know a line in the plane, so I'll highlight the line in our diagram here. There's our line that we're given. We can always find a point on that line, and we can also find a vector in the direction of that line by looking at the expression for the line. So if I look at the expression for the line, what I get is I get the vector that points in the direction of the line that I just read off by those values in front of the parameter t. So we have a direction vector that's -3, 4, and 2. And we also know a point on that line that is 7, 3, 5. And with that point and the other one we know, we can get another vector parallel to the plane. And that vector is going to be the vector from Q to P. So that's going to be the point P, which is 2, 4, and 6, minus the tail, which is the point Q. That's 7, 3, and 5. So we get a vector -5, 1, and 1. And now from those 2 vectors, we can get a normal to the plane. What's our normal to the plane? It's going to be the cross product of these 2 vectors that we have parallel to the plane. So it'll be this V cross this QP. So I'll just write down our memory aid for getting this cross product. So that's V -3, 4, 2, and the other vector -5, 1, 1. And so that gives us our vector 4 minus 2 is 2. And then the next one we get -3 times 1 minus 10, or 7, but then it's negative that because it's the middle term. And then the last component is -3 times 1, which is -3, minus 20. So -3 plus 20 is that vector there. So we've got a 2, -7, and a 17. And therefore, the plane is given by, we have a point on the plane, which is our point P. I'll highlight that in the question again. We have a normal vector to the plane. And so our equation to the plane is given by the normal vector dotted with an arbitrary point xyz minus the point we know. So I'll move this over a bit so I can fit it all in. So x minus 2, y plus 7. Sorry, I'm looking at the wrong thing. X minus 2, y minus 4, because that's the y coordinate of the point we know, and z minus 6, and that's equal to 0. So that's our equation of our plane, and we could write it as 2 times x minus 2 if we actually compute the dot product, minus 7 times y minus 4, plus 17 times z minus 6 is equal to 0. So there's our equation of our plane. So there's a little bit of work to be done on this one. We had a point on it, and we had a line that was contained in the plane, and so we just needed to know that we were able to find the normal vector to the plane doing this. Okay, now we're into these next examples. Let's find the angle between the following planes. Okay, so the angle between the following planes. What is that? So the idea with the angle between the planes is we've got a couple of planes here. I'll sort of sketch them like this. We've got a couple of planes, and the idea is that they are going to intersect along some line of intersection. And we're interested in the angle made by the two planes. So we'll indicate that in this picture. So what does that look like? Well, there's this line in the plane, and this line in the other plane, and that's the angle we're interested in. So how do we find that? Well, the key observation with finding the angle between these two planes is to take sort of a side-on view of the intersection so that it looks like this. So we'll look at this as a side view. And we're interested in the obvious angle that's given in that diagram. But the problem is we need to find two vectors in each of the planes and try to get them so that they are situated in such a way that we can work out the angle, and that's the same angle as the angle between the planes. But instead, if we focus our attention on normal vectors, then I could look at the normal vector to the first plane. Maybe I'll call that n1. And then I can look at the normal vector to the second plane. Maybe I'll call that n2. And those are easier to find because we can read those off as just the constants in front of the variables in the corresponding expressions, the coefficients of the x, y's, and z's. So we can read these values off. And the observation is that if I look at the angle between these two vectors, between the two normal vectors, that's the same as the angle between the two planes. These are the same. There was just a rotation that happened by 90 degrees, but the angle is still the same. And so that's what we're going to look for. We're going to look for the angle between the two normals. So the angle between planes is the angle between the normals. And so let's work out what these normals are. The normal to the first one, we get it by just reading off the coefficients of x, y, z. What's the angle, or sorry, the normal to the second plane? Again, we look back at the equation of the plane and we read off the corresponding coefficients, 2, 3, -2. And so now we can find the angle. We have that the cosine of the angle is the dot product of the two vectors divided by their lengths. And so the dot product is 6 minus 6 minus 2. And then the lengths are 9 plus 4 plus 1 and 4 plus 9 plus 4. And so that gives us then minus 2 over root 14 and root 17. And that is cosine of theta. So theta is arc, as I said, arc, I wrote car, arc cosine of -2 over root 14, root 17. And so there is an expression for the angle, which we can then work out. Okay, any questions? Oh, I see a question. Is that supposed to be IJK? Oh, yeah, I see where you're looking. Up here is, yeah, I, J, and K. Oh, K, thank you, K. Thank you for that. Yeah, that's supposed to be a K up there. Let me rewrite it. So we've got a K, and that's supposed to be a 2. Yeah, thanks for that. Okay, how about part B? Find the
Hello?
parameter. Hello, go for it.
Hi, Professor. Where did you get x minus 2, y minus 4, and z minus x, z minus 6 from?
Okay. So let's scroll back to the equation of a plane. So that's this one here. The equation of the plane, it's coming from this expression that says if you know the normal vector to a plane and you know a point on the plane, that's given by its position vector, then any other point, here we're writing down the position vector of that any other point, so this would be the x, y, z, is given by n dot this r minus r naught is equal to 0. So the idea there is we've got our plane, we know our normal vector, and I have it through a point. Let's say that's r naught, so that's going to be just our position vector from the origin. I should have moved my origin over. So there's our origin in our space. We got r naught, and now the key is we want to find a condition on any other point. So if that any other point we call x, y, z, then r is the position vector for that point. So it's also given by x, y, z. And then if I look at the vector that goes from r naught to r, it's got to be perpendicular to this vector n. And that's going to completely characterize all the points on the plane, is that the vector that goes from a point on the plane that you know to one that you're trying to come up with a condition for it to be on the plane, that vector, which is a green vector, has to be perpendicular to the normal for all x, y, and z. So that tells us then that we have the normal vector, which I'll call, let's say, ABC. ABC dotted with x minus the r naught value, so we'll call that x naught, y minus the y naught value, and z minus the z naught value is equal to 0. And then if we just take the dot product, that's where this expression down here comes from, this expression for the plane. So what that means is, if I'm going to write down the expression for a plane, what I just need to know is the normal vector, ABC, and some point on the plane, x naught, y naught, z naught. And if I know those two bits of information, I can put it into this formula and get the equation of the plane. And so that's what I've done down here. I took the normal vector, which was 2, -7, and 17, and I threw those values in front here. And then I took the point that I knew, which is up here, point P, which is 2, 4, 6, and I threw those in here. 2, 4, and 6. So I got an x minus 2, a y minus 4, and a z minus 6. Does that help in answering your question?
Yeah, it does. Thank you.
You're welcome. Okay, let's look at B. Find the parametric equations of the line of intersection. So for the line of intersection, we are looking for this plane and this plane and the corresponding x, y, and z values which live on both planes. So to do this, what we can do is we can write down the set of all solutions. So we'll solve this linear system. And the way we can do that is we can write down the matrix that represents the linear system and use our row reductions. The thing I'm going to do, though, is I am going to bring it so that the z value is first. And you might say, well, why am I going to do that? I'll write it down first, and then we'll see. So I'm just rearranging the order in which the variables appeared. That's 5 and 3. And the reason is because there's a coefficient of a 1 in front of the z. And if there's a coefficient of 1 in front of the z, it makes my elimination of variables a little bit easier to deal with. So I've got a 1, -2, 3, and a -2, 3, 2. And this is the z values, the y values, and the x values. And then I'll augment that with 5 and 3. And now at this point, we can do our Gaussian elimination. So I'm going to take 2 times the first row and add it to the second. It's that reason that I chose the z the z variable to be first, because it makes this calculation a little bit easier. I just have to go 2 times the first row added to the second to wipe out that z value in the second row. And so 2 times -2 is -4, added to 3 is -1. 2 times 3 is 6, plus 2 is 8, and 2 times 5 is 10, added to 3 is 13. And then at this point, I can take that one, well, maybe I'll write down the second row as this. I'll just multiply through by -1. That puts a 1 there in the y position of the second row. And then I'm going to take -2 times that second row, actually just 2 times the second row to add to the first row, because I need to wipe out that -2. So 2 times the second row added to the first row. 2 times -8 is -16, added to 3, -13. 2 times -13 is -26, added to 5 is -21. And so at this point, we get that z is equal to -21 plus 13x, but x I'm going to take to be my parameter t. Y is equal to -13 plus 8 times the parameter t, and x is my parameter t, or my free variable. And so that tells me then what the parametrization of the line is. X is equal to t, y is equal to -13 plus 8t, and z is equal to -21 plus 13t. So that's the line of intersection. It gives us a vector in the direction of the line. We can read that off, 1, 8, 13, but we also get a point on the line just by plugging in t equals 0, 0, -13, -21. So we can extract that information from this line, points, and the direction that it points in. Okay, last one. Find the distance from the point 1, 2, 3 to that plane. So here we want the distance from the point 1, 2, 3. I'll just jot that down. 1, 2, 3 to the plane, and the plane is given by 3, negative 2, 1, 5. So 3x negative 2y plus z is equal to 5. Okay, so distance from a point to a plane. This is going to be the same idea that we used when we found the distance from a point to a line. So what I'll do is I'll just jot down a picture. We can maybe think about how we're going to get this distance. So I've got a plane and I've got a point that's not on the plane. How do I know the point's not on the plane? We can just plug that point in, 1, 2, 5, into the equation. So if I plug in x equals 1, y equals 2, z equals 3. So plugging in 1, 2, 3 into that plane, we get 3 minus 4 plus 3, or 6 minus 3, which is not 5. So it doesn't satisfy the equation of the plane when you plug it in, so you know it's not on the plane. If it was on the plane, then the distance between the point and the plane would be 0, because it lives on the plane. But this point is not on the plane, so we want to find its distance. So we're interested in some sense, what is that distance there? There's going to be a right angle. That's our question. What is that distance? The shortest distance from the point to the plane is going to be along that line segment that makes a right angle with the plane. Well, the idea is that we know a normal. So I'm going to draw the normal just somewhere else so we can get a visual for what's going on here. So we know that normal to the plane. That normal is given by 3, negative 2, 1, just by looking at the equation of the plane. Now what I can do is I can project the vector, let's call this point Q where we're taking the normal at. It really doesn't matter too much at this point what that point is, just to get our argument down. I can look at that vector that goes from that point Q out to that point P, and then I can take its projection onto the normal. And that projection is, well, the length of this projection is just the length of this vertical line segment going up from the point under P on the plane up to it. So the idea is that this projection vector has magnitude, which is the distance from the point to the plane. So we need to find the projection of the vector QP onto the normal vector. That's what we want to look for. And then we take its length, and that'll give us the distance from the point to the plane. Okay, now in order to do this, we have to have components for that vector QP, which means I do need to know what that point Q is. Now that point Q can be anything. I just pick it to be anything. Any point on the plane I can take to be that point Q, and then I just sort of move the normal so it sits at that point Q, and then do the projection onto that vector. So in order to get that point Q, we just have to look at the equation for the plane and try to spot a solution for x, y, and z. So just find any point whatsoever on the plane by just looking at the equation. And I find this most easily done. Can you use the distance formula for between 2 points? The answer, in short, the answer would be, yeah, you can use the distance formula. The only issue is that I want to find the distance between this point and this point down here, which lives along the vertical line, or this line segment that's orthogonal to the plane. So if I did know what this point was, then yes, I could use the distance between the 2 points. The problem is I don't know what that point is down there. What I could do, and I'll just give you sort of a synopsis of how you could find that point. You could say, well, I know the point P. I know the normal 3, -2, 1. So that would allow me to construct a parametric equation for the line that passes through the point P and goes in the normal direction to the plane. So in other words, I could find a parameterization for this line, and then I could take that parameterization and determine where it intersects the plane by plugging it into the equation of the plane, solving for the value of the parameter. Once I know the value of the parameter, then I can get the point on the plane, which is that question mark, and then I can use the distance formula to find the distance between 2 points. But it takes a bit to do that. I mean, that's a lot of work, where we will see in just a second doing this projection that we cut our work down immensely. We don't have to do much calculation in order to do that. So this is a much more efficient way in terms of the calculations involved. So we find a point on the plane, and I'm just going to pick 0, 0 as my first two coordinates of the point, and then just whatever the z value is that it has to be in order to live on the equation of that plane. So if x is 0 and y is 0, then the equation becomes z equals 5. In other words, q is 5. Now the benefit of this method is I just need any point on the plane. I don't have to go through and find the coordinates of that point I labeled with a question mark. I don't have to find the point directly underneath P. I just pick any point on the plane, the easiest one there is to find, which I found it. And now I do the projection of the vector QP onto the normal vector. And so that projection is, maybe I should write down what QP is. We are doing the projection onto the normal vector of the vector QP. So that would be P minus, or 1 minus 0, 2 minus 0, and 3 minus 5 is -2. So that's the vector we're projecting onto 3, -2, 1. And so in order to do the projection, what we have to do here is we have to compute their dot product. Maybe I'll just put this as, in sort of parentheses here, because I'd much rather just work with variables for the first little bit to see what things simplify down to, rather than using numbers. So I'm going to just write down what the formula is for the projection. That is vector QP dot n over the magnitude of n squared, and that's the component of the projection, and then that's times the direction that we're going in, which is n. So that's the calculation we need to do. The dot product of the two vectors divided by the length of the vector squared times the length. But I'm not actually interested in the projection vector itself. I'm interested in the length of the projection vector, because that's the distance. So I'm really interested in this, which means I'm really interested in QP dot n over the length of n, the length of n squared times that, so, and the magnitude of that thing. And that means I'm interested in QP dot n in absolute value over, well, when I take the magnitude of this, I get the magnitude of n on top, and then I got a magnitude of n squared on the bottom, so that just gives me a magnitude of n. So that's really, this is the calculation we have to do right here. That's it. That's how we find the distance. So we find an arbitrary point Q, and we know the normal vector, and so we just take the dot product of Q, P, that vector, with the normal vector, and divide by the length of the normal vector. So now I can use the values here. So the dot product of QP with the normal vector is 1, 2, -2, dot the normal vector, which is 3, -2, 1, all over the, and that's in absolute value because we're looking at a length here. And then that's all over the length of the normal vector, which is the square root of 9 plus 4 plus 1. And so that gives us the dot product gives us 3 minus 4 minus 2. So 3 minus 6, or negative 3 in absolute value, which is 3 all over root 14. And that is the distance from P to plane. Okay, so the idea here, as I said, was we don't have to search for that point directly under P. What we do is a projection of the vector onto the normal vector and compute its length. Yeah, so that's a good question. Vector projection versus scalar projection. This here is the vector projection. Because what we did was we found, maybe I should put that in green because in our diagram, that's what it is. So this is that vector in the diagram. So that's our vector projection. And the piece right here oh, sorry, not that one, because I got to worry about the square. So I will dot these out. Okay. So what is the scalar projection? The scalar projection is QP dot n over just the magnitude of n. That's the scalar projection, and that's precisely what this is here. That's our scalar projection. So your question was, is that just the scalar projection? The answer is yes. The distance from a point to the plane is obtained by taking the scalar projection of a vector that points from an arbitrary point on the plane to the point P, and does a scalar projection onto the normal vector. Okay, where are we now? We've just finished now our stuff on equations of lines and planes. So you can see how the geometry, it does depend a lot on dot products and cross products. And so that's what we're going to be extensively using. Sorry, I've got a dog here that's coming to my feet, so I got to move him over. He escaped from his little pen. Okay. So we can see that the geometry in 3 dimensions requires us to work with dot products and cross products and projections and the like. So those are going to make our toolbox up for doing the geometry of objects in 3-dimensional space. Okay, now what I want to do is I want to talk a little bit more about objects in space and how to represent them. So for us, the first or the next step along this line is going to be space curves, also known as vector functions, but we'll refer to them as space curves here because it's the natural extension of a line. We saw that a line was obtained by a parametrized form, so taking a particular point and then taking multiples of a direction vector, and that was able to construct the line in space. But we can do this with other functions as well. They don't have to be necessarily linear functions. So for example, let's describe the motion of a particle whose coordinates at a given time t are x equals cos of t, y equals 0, and z equals sine of t. So what is this going to look like? We'll jot down our coordinate axes here. This is x, this is y, and this is z. As t varies, what we're going to be doing is we're going to be plotting various points. So for example, when t is equal to 0, we get cos of t is 1. So we're out here along the axis at 1. Y is 0, and sine of t is 0. So we're at a point here. And then as t starts to increase, what happens? Well, the x coordinate starts to increase. The y value is always 0, and the x coordinate starts to decrease because it's cosine, and then the sine value starts to increase. So what we end up getting is something that looks like this. And what that is, that's a circle in the XZ plane. Okay, so I just want to show you that we're coming back to 12.6. Yeah, we're skipping it for now, but we're going to come back to it. So I want to show you that we can plot these things. As I said, I do encourage you to play with the plotting tools to get good visuals. So we're interested in a parametrized curve. And the parametrized curve is cos of t 0 and sine of t. And so what we'll do is we will plot that. So it's already plotted there. Oh, did I? Y equals 0. What are we? There we go. I got to switch my vision here. The other thing I have to do, as I said, when we do plot, is I have to make sure that all the scales are set the same. So that's under axis and camera. Now I'll go back to main. And we can see that the parametrized curve is indeed a circle in the XZ plane. So these are the kinds of objects that we are going to be playing with, and we're going to do calculus on these as well. So we're going to look at these curves and find tangent lines to them. We're going to do that through the notion of a vector. So if you think about back to calculus 1, where we talked about parametrized curves in 2 dimensions or in the plane, we are now just ramping that up and we're doing it in 3 dimensions. And then we're going to talk about the calculus involved in that as well. So that's where we're at. So a parametrized curve is a triple of functions, x equals f of t, y equals g of t, z equals h of t, where each of those functions is just a function of a single variable with a real value output. And so what we're doing is we're thinking of it as space x, y, z, and this thing as capturing the motion of a particle as it maybe moves through space. So at a given point, its coordinates are given by f of t, g of t, and z of t. So that's what we are describing now, a way to construct curves in space or describe curves in space. Okay. Let's have a look at an example. Describe the motion of a particle whose position vector is given by r of t is cos of t I hat sine of t j hat plus t k hat. So again, it looks like if I just focus on these two, cos of t and sine of t, those are our circular functions. Those are really cos and sine together are what we use to parameterize circles. So this is going to be a circle. I'll put it in quotes because we'll see what actually happens. It's a circle parallel to the x y plane. Because if I just imagine I ignore the z component for a second and I just think of it as 0, then it's a circle in the xy plane. But if I let the t value vary, then it allows the z point or the z coordinate to creep up. And so let's get a feel for what that actually is then. So here's x, y, and z. So we are at, and when t is 0, we're at this point. What typically would be a circle, if the z value wasn't changing, that would look something like this. It's not because the z value is changing, so what's happening is it's actually going up the axes and doing things like this. So it's traveling up the axes and it's spiraling around it. And similarly as it's going down as well. And so what we get is what's called a helix. This spiraling thing around the axes. So let's go ahead and plot this and see that it is what we think we ought to be getting. Okay, so we've plotted it now, and we get that spiraling motion. And the point is that we're not getting to line up, of course, because of perspective. This stuff on the top is closer to our eye, so that's why it looks bigger than the stuff farther away. But the idea is that there's this spiraling motion going around. It's just circling around the z-axis, and it's moving up as you go around. So we start at this point, t equals 0, and it's just spiraling around the axes. And so this is what a helix is. And now we've got the expression for working with the helix, and that's given by the cosine and the sine and that linear function t. Okay. So a vector valued function, which is the title of the lecture, is just any function that associates with the number t a vector, in this case r of t, called the vector value of the function, or the vector valued function. What we tend to think of this as, if we think of r as a function, and we write it using our input-output notation, then r is a function where the inputs are real numbers, that's the value t, and what's coming out is a vector, a three-dimensional vector. So we usually write this as sort of a boldface v, like this, a sort of a v with two bars on the side. And what this vector space v is it's just the set of all three-dimensional vectors where x, y, z is in R. Okay, you may say, why didn't I write R3 there instead of V3? The reason I didn't write R3 there is because R3 for us is usually denoting the set of points, but I want the output of this function to be a three-dimensional vector, not a point. So this set V3 represents the set of all vectors with the angle brackets, whereas R3 would represent the set of all points with round brackets. It's a distinction that we tend to make in this class, but as you move forward in your mathematics and other courses, you won't really make that distinction to apparent. You sort of blend the idea of R3 and V3 together. It's not such a big deal, but here we'll make the distinction between angle brackets and round brackets. So once we've got a notion of a function, we can look at things like what is the limiting value of a function as the input approaches some value. And so we can look at the limit as t goes to a of r of t. And in this case, since r is just made up of three functions of a single variable, then we can translate that notion of a limit to one of a limit from calculus 1 by just looking at the limits of the individual component functions. So that's one thing we can just note, that limits are component-wise. You may say, well, why are we needing limits? Well, limits are, for one thing, they allow us to characterize whether things are continuous or not. If the limiting value is equal to the value you get by just plugging that value into the function, then it's continuous. But they also allow us to compute things or define things like derivatives, and then we will develop calculus on curves using this notion of a derivative, which comes from a limit. So the first thing, though, that we would use a limit for is to talk about whether a curve is continuous or not. And a curve is continuous at a point A, provided that the limiting value as t goes to a of r of t is just r of a. And so since r is equal to f, g, and h, then r is continuous if and only if f, g, and h are continuous. So that just reduces this question of continuity of a curve to continuity of the three functions that make it up, and those are functions from calculus 1. They're functions of a single value, a single variable with a real value coming out. So that's back in the realm of what we're used to dealing with. Let's find a vector equation now. So let's find an equation representing a curve. So here we've got a set of points, P and Q, and what we want to do is we want to find the vector equation and the parametric equation for the line segment that joins P and Q. So this is a line segment. I don't want it to extend beyond those points. I just want to capture from P to Q. I want to get that line segment. And so how am I going to do that? Well, the first thing to do is to get a vector that points in the direction of that line segment. So that's what we'll call V, and that's going to be from P to Q. So that's going to be 1 minus 4, or negative 3, negative 1 minus 1, that's negative 2, and 2 minus 7, that's negative 5. Oh, I got all negatives there. Maybe I should have gone from Q to P and done the opposite. Doesn't matter. I've got a vector now that points in the direction. I also know a point on the line segment, that's P. So I'd like to get the line segment. So I will represent it by, I'll call it L instead of R in this case. I'll call it capital L, the vector function. And I want to allow this parameter t to be plugged into this function and it to give me the points on this line. So if I start with the point P, let's pop this thing in here.
Hey, Jamie, your 2 should be positive.
Negative 1, so Q, oh yes, 1 minus, thank you, good. And it's not so bad if all of them aren't. Thanks very much. 2. Okay, so what we want is we're going to start at that point P. So there's our point that we're at, 1, negative 1, 2. And then I want to add to that multiples of my vector V that points in the direction. Now what can we do in this case? So I don't want all possible vectors V. I don't want to add all possible multiples of the vector V. In other words, I don't want a negative V to be added to this point because then it would be pointing in the opposite direction. And, it would come down here and construct a point there. So what are the values of my parameter that I want? Well, I want to take t times this vector that points in the direction of the line. So that's negative 5t. So that actually gives me the whole line.
Sorry, Dr. Mahula, it's
Yeah.
Nilüfer. So for vector V, is it like it's going to be Q minus P or P minus Q? Because I think if it's Q minus P, that they're saying.
Oh, I've got another error there, right?
Yeah.
Yeah. So this is Q minus P because it's tip minus tail. So let's see.
Yeah.
4 minus, I got a bunch of them wrong, didn't I? Thanks. Let me write it out again. Q minus P. So 4 minus 1, 3. 1 minus minus 1, 2. 7 minus 2 is 5. Thank you. Yeah, I got a bunch of them wrong. Thank you very much. Just making sure you're all awake, right? Not really, just making sure myself is awake, I guess. Okay, so we got them here. 1, negative 1, 2, and then 3, 2, 5. That looks good. So this is going to give us the entire line. Right? I'm going to draw a dotted portion out here and out here. That'll give us the entire line. We don't want the entire line. We only want the segment from P to Q. So that means we only want the values of t to be at least 0, but we don't want that value of t to be any bigger than 1. we don't want to be adding a multiple of v that's any longer than v itself. So this is v here. So we want all of the points that live on this segment out to where this is p plus 1 times v. And this is p plus 0 times v. And then we want everything between 1 or 0 and 1. So that is our parameterization of the line segment. Okay. So here with...
Hello, Professor.
Hello, go for it.
Can you explain one more time why we want t between 0 and 1?
Ah, sure. Let me just go here and plot it, and we'll see what happens. So this is going to be 1 plus 3t, negative 1 plus 2t, and 2 plus 5t. Okay, so that's the line that we've got that passes through the point P and Q. So let me just add the point P and the point Q to our diagram just so we can see. Point P is 1, negative 1, and 2. And the other point is 417. 417. Okay, so those are our 2 points, and we just want the line segment that goes between them. So now, notice if I change the t value, let's say negative 1 to 1, my line segment's getting shorter. And what does that mean? Well, what this means is I've got this vector. I'll put the vector in, and this is the last thing we'll need. I've got this vector 3, 2, 5, which points in the direction of the line segment. And I will move it so that its tail is now at the point P, which is 1, negative 1, 2. Okay, so that's our vector. You can see the tip of it up there. And what I want to do is I want to take all multiples of this vector so that I can start at this point P and get all the way out to the point Q. The problem is if I allow for a negative multiple of that vector, which I'm allowing here, I'm allowing my point P plus a negative t here times the vector, it's giving me this point down here because that's the point P plus negative v. But I don't want to allow points that are not between P and Q. So I only want the points between P and Q to survive. And so those are the ones that are going to be from, let me just drop this in here. I will go from T, and let's see if I can be a little bit more fancy here. I will put a slider in place, capital T. We will start it from 0. We will end at 1, and we will put our slider T here, and let's see if we're going to be able to get it. T equals, oh, I was hoping it was going to work right off the bat. I might have to think about this a little bit more as to how to get my slider to work.
So you need to remove the vector from, because your vector is on top of the
Oh, my
graph.
vector's on top. Thank you. There it is. Yes, perfect. Thank you. So there we go. So that's when t is equal to 0. So in our parameterized curve. And then as I let t increase, so now I've got t equals 0.3. What this is doing is it's taking the point P and adding 0.3 times the vector v to it, which gives us basically a third of the distance along here. And then if I add half, the value half for t, that's half of the vector v. So that's exactly halfway between it. And I want to end up at q, so I've got to go all the way out to 1. If I extend beyond 1, now I'll add another value there, then I'd extend beyond. That'd be twice the vector. And if I allowed negative values in for t, then I would extend in the other direction. So I just want to restrict myself to values of t which are between 0 and 1 in order to trace out that line segment. Does that make sense? Is that it?
Yeah, it does. But how do we calculate that though? How do we like find out that the boundaries have to be 0 and 1? You know what I mean?
Because we've just constructed our vector v.
Sir?
Okay.
and I'm hiding that. Yeah, yep, go for it.
Are we like finding like when t equals to 0 we get the point P, and when t equals 1 we get the point Q? So are we like basically using those values as the upper and the lower limit?
You are. So I'll write this in a
Okay.
slightly different way. So for L of t, for that line, we are starting with the point P, and we are adding to that the vector from P to Q. And so this is a way I don't like to write it because I'm writing points and I'm doing addition of points, but this might help you think about it in an appropriate way. So how do we get the vector PQ? We get it by taking Q minus P. So again, these are points, but, and I don't like writing it like this because I should really be using vectors here if we're going to do addition of them. But the idea is that I'm starting at my point P, and then I'm adding a multiple of this to it. And so when t is 0, I'm at my point P. And then when t is equal to 1,
P minus P equals 0. Okay.
you got it, yeah. And you just get the value Q. Yeah. So that traces out everything from P to Q. Does that help?
Yes.
Okay.
This helps.
Yeah, that helps. Thank you so much.
You're welcome.